Welcome to Fluid Mechanics and Hydraulic Machines Laboratory. Today we are going to conduct an experiment to determine the hydraulic coefficient in a small vertical orifice. A vertical orifice is a small opening in a tank which is at a depth of 1/3 from the bottom of the tank. The different hydraulic coefficients are coefficient of velocity, coefficient of contraction and coefficient of discharge. Coefficient of velocity is defined as the ratio of actual velocity of jet at vena contracta to that of the theoretical velocity of jet. Vena contracta is a point in the jet which is at a distance of 0.5 times the diameter where the flow lines will be parallel. Coefficient of contraction is defined as the area of jet at vena contracta to the area of orifice. Coefficient of discharge is defined as the ratio of actual discharge from an orifice to the theoretical discharge from the same orifice. This is the experimental setup of the vertical orifice. As you can see, the vertical orifice is a circular hole in a laminar section which is attached at the bottom of the overhead tank. The orifice dia can be varied from 10 mm to 12 mm as you can see. The slider gauge is used to measure the vertical and horizontal coordinates in the jet with respect to point of vena contracta and the point of bend. Switch on the pump and allow the water to flow through the vertical orifice. After a constant head is attained in the overhead tank, note down the horizontal and vertical coordinates with respect to vena contracta. You can see the vena contracta is a point in the jet where the flow lines will be parallel to each other. Note down the vertical and horizontal coordinates with respect to the point of vena contracta using the slider gauge. Note down the reading as x0 and y0 with respect to point of vena contracta. Shift the pointer gauge to the point of bend of the jet and note down the vertical and horizontal coordinates as y1 and x1. Close the outlet of the collecting tank and note down the time taken for a 10 cm raise of water level in the collecting tank. For different discharge condition in the overhead tank, note down the horizontal and vertical coordinates. The observation and the calculation part of the vertical orifice is as follows. Firstly, the diameter of the orifice is taken as 10 mm, which is 0.01 meter, and the cross-sectional area of the orifice is given by the formula pi d square by 4. Therefore, the cross-sectional area of the orifice will be 7.854 into 10 power minus 4 meter square. The breadth of the collecting tank is 0.3 meter and the length of the collecting tank is 0.4 meter. Therefore, the area of the collecting tank is the product of the breadth and length of the collecting tank, which is taken as 0.12 meter square. The theoretical discharge through a vertical orifice is given by the formula Q theoretical is equal to A0 into square root of 2gh, where A0 is the cross-sectional area of the orifice, which is 7.854 into 10 power minus 4 meter square, and G is the acceleration due to gravity, which is taken as 9.81 meter per second square, and H is the head acting in the orifice, which is 0.4 meter. Therefore, by substituting the A0 and G and H value, the Q theoretical will be 2.2 into 10 power minus 4 meter cube per second. The actual discharge through a vertical orifice is given by the formula Q actual is equal to A into R by T, where A is the area of the collecting tank, which is taken as 0.12 meter square, and R is the rise in the water in collecting tank, which is 0.1 meter, and T is the time taken for the rise in water level. The rise in water level for 10 centimeter was 84 seconds. Therefore, by substituting the A, R and T value, the Q actual is 1.428 into 10 power minus 4 meter cube per second. The actual velocity is given by the formula V actual is equal to Q actual by A0, where Q actual is 1.428 into 10 power minus 4 and A0 is 7.854 into 10 power minus 4. Therefore, V actual, that is the actual velocity, is 1.818 meter per second. The theoretical velocity is given by the formula square root of 2gh, where g is the acceleration due to gravity, which is 9.81 meter per second square, and h is the head acting in the overhead tank, which is 0.4 meter. By substituting those values, V theoretical will be 2.801 meter per second. The hydraulic coefficients are coefficient of discharge, coefficient of velocity, and coefficient of contraction. The coefficient of discharge is given by the formula Q actual by Q theoretical, that is actual discharge to the theoretical discharge. By substituting the actual discharge as 1.428 into 10 power minus 4 and theoretical discharge as 2.2 into 10 power minus 4, the coefficient of discharge will be 0.64. The coefficient of velocity, which is CV, is given by the formula x divided by square root of 4 by h, where x is the horizontal coordinate and y is the vertical coordinate. Or else, the coefficient of velocity can also be calculated by the formula V actual by V theoretical. The horizontal coordinate x1 with respect to the vena contracta is 0.07 meter, and the horizontal coordinate with respect to the point of bend is 0.143 meter, where x is given as x2 minus x1, which is 0.073 meter. Y1, that is the vertical coordinate with respect to the point of vena contracta, is 0.0987 meter, and Y2, that is the vertical coordinate with respect to the point of bend, is 0.1068 meter. Therefore, Y is equal to Y2 minus Y1, where the Y value will be 0.081 meter. By substituting the x and y value with respect to the coefficient of velocity equation, the coefficient of velocity will be 0.66 meter. Or else we can also calculate the coefficient of velocity as V actual by V theoretical, where the CV value will be 0.66 meter. The coefficient of contraction is given by the formula ratio of coefficient of discharge to the coefficient of velocity, where the coefficient of discharge is 0.64 and the coefficient of velocity is 0.66, where the coefficient of contraction will be 0.98. The coefficient of contraction is higher because the inside surface of the vertical orifice is sharp in nature.